where we're breaking down a masterclass on wheel alignment geometry. Listen, if you've ever spent hours chasing down a frustrating mystery pull, or had to deal with a completely crooked steering wheel right after a fresh alignment, or maybe you just want to squeeze every last ounce of grip out of a track car, well, you're in the exact right place. Because today, we're going way past those basic green and red numbers on the alignment screen. We're getting into the actual, physical geometry that drives those measurements.
So here's our game plan. We'll start with the dynamic triangle, then move into visual diagnostics. From there, we'll hit the definitive 10-step professional sequence, get into some advanced track tuning, and finish up with special troubleshooting.
The source material kicks things off with this absolutely brilliant concept. Alignment is a living system. And honestly, it is so incredibly important to grasp this. Alignment isn't just a set of static numbers on a spec sheet. Not at all. It's this continuously interacting, dynamic system that changes with literally every single suspension compression, every degree of body roll, and every bump in the road. When you tweak just one angle, you're fundamentally changing how that vehicle breathes and moves down the highway.
All right, Section 1, the dynamic triangle. Let's look at how camber, caster, and toe actually interact when a car is in motion.
We'll start with camber. Now, we all know negative camber tilts the top of the wheel inward, right? But why? Well, it's all about optimizing that tire contact patch during body roll. And this brilliantly illustrates this awesome concept called camber thrust. Basically, a cambered wheel naturally wants to roll in the exact direction it's tilted. Think about how a motorcycle leans into a turn. It's the same idea. So, a negatively cambered tire that's being pushed into a corner actively generates additional lateral cornering force. It actually improves your grip exactly when the suspension compresses and you need it the most.
Okay, next up is caster. That's the tilt of your steering axis. Positive caster creates what we call mechanical trail. It's essentially dragging the tire behind its pivot point, kind of like a shopping cart wheel. That trail is exactly what gives you that heavy, strong steering feedback and solid straight line stability. But here's where the real magic happens: caster-induced camber change. When you turn that steering wheel, positive caster automatically generates negative camber on the loaded outer wheel. It is just an elegant geometric interaction. It maximizes your grip dynamically, and it does it without requiring any suspension travel whatsoever.
Then we've got toe, which is there to pre-compensate for the dynamic changes caused by rolling resistance and suspension compliance. As you can see, front toe in gives you fantastic straight line stability, which is, perfect for everyday road driving. But if you're taking a car to the track, a slight front toe out gives you a much sharper initial turn-in. Now, it does sacrifice some of that straight line stability, and it can definitely promote oversteer on corner entry, so keep that in mind. Oh, and don't forget the rear axle. If you've got soft suspension compliance in the rear, those wheels can dynamically toe out under hard cornering, giving you some really unexpected oversteer tendencies.
Before we move on from geometry, we absolutely have to talk about scrub radius. This is the distance between where your steering axis hits the ground and the actual center of your tire contact patch. So why does this matter to us? Well, say a customer comes in with some massive aftermarket wheels with totally incorrect offsets. That instantly alters this geometry. A compromised scrub radius will dramatically mess with your steering feel, it'll amplify braking forces side to side, and it can literally ruin the car's braking stability. Moving right along, Section 2, Visual Diagnostics and Handling Symptoms. Let's take all that dynamic theory and translate it into visual evidence you can actually use on the shop floor.
A technician's absolute best diagnostic tool is often sitting right there on the rim, the tire itself. Inner edge wear, that points to excessive negative camber. Outer edge wear, you're looking at excessive positive camber. But the real trick is reading what we call feathering. The source material gives us this fantastic tactile tip. Literally run your fingers laterally across the tread blocks. If they feel sharp, like a saw blade pointing inward toward the center of the car, you've got a toe-out error. If those sharp edges are pointing outward, you're dealing with excessive toe-in.
And that brings us to this highly useful diagnostic cheat sheet. If a vehicle has this really vague, wandering steering feel, your primary suspect is insufficient positive caster. Now, what if the steering just refuses to return to center after a turn? That poor self-centering is a classic telltale symptom of either incredibly low caster or you've got mechanical binding in the steering rack or ball joints. And hey, if the driver is complaining about corner exit oversteer, check that rear toe immediately. Even a tiny bit of rear toe out will make a car incredibly tail happy. Okay, Section 3, the 10-step professional sequence. Doing an alignment in the wrong order practically guarantees a comeback, so let's run through the definitive professional workflow.
Notice how the first 4 steps happen before you even think about picking up a wrench? The sources really stress this essential safety and inspection checklist. I mean, trying to align a car with a worn tie rod is literally impossible. So inspect the components, correct the tire pressures, verify the ride height, and then, this is key, perform the suspension bounce test. You need to physically push down on the front and rear bumpers for 3 full compressions. This properly settles those suspension bushes into their natural resting state before you take a single measurement.
So the crucial point here is the exact adjustment order. Start at the rear with camber, then set the rear toe. Move up to the front to set camber and caster, and your front toe is always, without exception, adjusted last. Why? Because the moment you adjust caster or camber, you physically move the steering knuckle, which inherently throws off your front toe. If you set front toe first, you're just going to completely ruin your own work the second you touch a camber bolt.
Let's see how this builds right into our next concept, the thrust angle. Remember how we just said to establish rear toe before front toe? Well, this is exactly why. Rear toe establishes the thrust line, which is the actual direction the rear axle is trying to drive the vehicle. Your front wheels have to steer relative to this thrust line, not just the geometric center of the car. If you fail to measure and correct the thrust angle, that's exactly how you end up with a car that dog tracks or crab walks down the highway and leaves you with a steering wheel that's permanently off-center.
Moving into Section 4, Advanced Performance and Track Tuning. This is where we toss the factory defaults out the window to optimize dynamic grip.
If you're looking at a street-driven performance car, you generally want a balanced approach. We're talking around -1 to 1.5 degrees of camber, maximize caster for that great steering feel, and a slight rear toe end for stability. But, and this is a big warning, if a customer insists on a highly aggressive track setup, like -3 or 4 degrees of camber, and then they try to use it for their daily commute, they will absolutely obliterate the inner shoulder of their tires. Track angles need massive lateral cornering loads to flatten out the contact patch. If you don't have those loads on a highway commute, you're basically just driving on the inner edge of the tire.
What's really fascinating here is how we can scientifically validate those track settings right there in the pit lane. You use a tire pyrometer to grab temperatures across 3 points: the inner shoulder, the center, and the outer shoulder. For a negative camber track setup, perfection is when the inner edge is slightly hotter than the center, and the center is slightly hotter than the outer edge. If that outer edge is boiling hot, you don't have enough negative camber and the tire is rolling over under load. And if the center is burning up, your tire is overinflated.
All right, we've made it to Section 5, Special Troubleshooting and EVs. Let's tackle those incredibly tricky diagnostic scenarios that usually leave workshop technicians scratching their heads. Electric vehicles are literally changing the game. Think about it. Their massive battery weight demands much more aggressive negative camber specifications. Plus, regenerative braking applies these incredibly powerful drag forces right through the driven wheels. That means your toe specs have absolutely zero margin for error, otherwise the car gets super unstable during deceleration. Now, what if you perfectly align a car, EV or gas, and it still has a persistent pull? The sources say to check your crosscaster side-to-side difference, make sure it isn't greater than ½ a degree. If that looks perfect, swap the front tires left to right. If the pull changes direction, boom, you've just diagnosed tire conicity, which is a manufacturing defect in the tire itself, totally unrelated to your alignment job. And we really need to highlight this critical post-accident warning from the source material. Bent components can easily hide behind perfectly green in-spec numbers. Seriously, if a vehicle took a hard hit to a curb, a bent steering arm or lower control arm might still let you force that toe reading into the green on the alignment machine. But the actual physical geometry, things like the Ackerman angle and the bump steer curve, will be completely destroyed. The car is going to handle terribly even if the computer screen is telling you everything is perfectly fine.
Which brings us to our final provocative thought for today. As a technician, are your perfectly in-spec alignment numbers secretly hiding a fundamentally compromised, bent geometry? It's a huge reminder that we always need to look beyond the computer screen. Get your hands dirty, feel the tire wear, test the self-centering, check the pyrometer data, and actually inspect the metal.